Imagine standing on an airport tarmac, looking up at a massive machine. It stretches over 70 meters long. Its wingspan is nearly 80 meters, about the height of a 20-story building lying on its side. And its total weight? Over 400 tons. That's the equivalent of 80 adult elephants. Yet in just a few seconds, this metal colossus lifts off the ground and ascends into the sky. It's not magic, it's physics. But even knowing that, the idea that something so massive can fly still feels unbelievable. The secret lies in a force called lift. It's the upward force that opposes gravity and keeps the plane in the air. Lift is generated by the shape of the airplane's wings, known as an airfoil. As the plane speeds down the runway, air flows around the wings. Because of their curved upper surface and flatter underside, air moves faster over the top than underneath. According to Bernoulli's principle, faster moving air has lower pressure. That pressure difference creates an upward force, lift, but lift doesn't happen on its own. It depends on speed. A massive aircraft like the Airbus A380 or Boeing 747 needs to accelerate to more than 280 kilometers per hour, about 174 miles per hour, just to leave the ground. The heavier the plane, the more lift is required, and the faster it must move. That's where the engines come in. Jet engines generate an incredible amount of thrust. They operate on a principle known as reaction propulsion, based on Newton's third law. For every action, there is an equal and opposite reaction. Here's how it works. The engine sucks in air, compresses it, mixes it with fuel, and ignites it. The resulting explosion blasts hot gases backward at high speed. That backward push creates a forward thrust that propels the plane. It's like releasing a balloon without tying the end. The air rushes out one way, and the balloon flies in the opposite direction. The same principle, just scaled up with tons of steel and thousands of liters of fuel. As the plane accelerates, the faster air flows over the wings, increasing lift. At the right moment, the lift becomes greater than the aircraft's weight, and it takes off. But flying isn't just about getting off the ground. It's about staying in control. The wings themselves are a masterpiece of engineering. They're shaped and angled to maximize lift while minimizing drag, the air resistance pushing against the plane's motion. During takeoff, pilots extend flaps and slats from the wings. These increase the surface area and curvature, helping generate more lift at slower speeds. Once airborne, the flaps retract, and the wings return to a more aerodynamic shape. Every gram of weight is calculated and controlled. Fuel is stored inside the wings. Cargo is loaded strategically. Even water in the lavatories and meals for passengers are accounted for in the weight distribution. Commercial airliners have strict limits on how weight is distributed, known as center of gravity. A shift of just a few meters can affect stability, making the plane harder to control. Then there's altitude. Commercial planes cruise at around 35,000 feet, more than 10 kilometers above sea level. At that height, the air is much thinner, which reduces drag. That's good for fuel efficiency, but it also reduces lift because there are fewer air molecules to generate pressure. So the plane must maintain high speed to compensate. At cruising altitude, a typical commercial jet travels at around 900 kilometers per hour. That's over 560 miles per hour. Even at that speed, the balance of forces is delicate. 4 primary forces act on the plane: lift up, weight down, thrust forward, and drag backward. If lift and thrust exceed weight and drag, the plane flies. If not, it falls. But what about turbulence? If a 400-ton aircraft can be shaken mid-air, how stable can it really be? The answer varies. Turbulence is simply irregular air movement, like waves in the sky. Planes are designed to flex with the air, not resist it. The wings of a Boeing 787, for example, can bend up and down by over 7 meters without damage. Flexibility isn't a weakness. It's what keeps the plane intact during storms and air pockets. Modern aviation is built on redundancy and precision. Every component is tested under extreme conditions. Pilots go through thousands of hours of training. Computers monitor every part of the flight. Even if one engine fails, commercial jets are designed to fly safely on just one. So how does a 400-ton machine stay in the air? Because its wings are shaped to create lift. Because its engines generate enough thrust to keep it moving. Because physics allows us to turn motion into flight. And because engineers have turned that physics into reality. Every time you sit on a plane and feel it leave the ground, you're witnessing the result of centuries of scientific progress. What looks like magic is actually the triumph of math, engineering, and human understanding. You're flying on a machine heavier than a tank, almost faster than a bullet, and more complex than most spacecraft. And yet it works. Every single day. Subscribe us for more videos.